We're now going to start talking about some physics principles. And this also ties into Newton because Newton studied light as well. So let's talk about light. And light is the very most important thing to astronomers, is understanding that, because we can't go to the stars and grab star material and analyze it in a lab. The only thing we get from these objects is light. And so that light, we have to understand what creates it, how it's created, why we see it the way we do, and then that helps us to infer properties about the object we're looking at. So let's talk about light. Light, we're going to talk about it as a wave. Now, when you get into really complicated physics, you find that wave can also act like a particle. I mean, that light can act like a particle and a wave, and has this particle-wave duality. But mostly the easiest way to understand it is that it's a wave. And it's a transverse wave, like this. Transverse wave means that the wave is moving in this direction, or a fancy way of saying it is propagating in that direction, but the oscillations are perpendicular to that. Now, we measure the wavelength, and we call that lambda, this Greek letter here. It's lowercase lambda. That's the wavelength. And the wavelength is the distance between successive crests of a wave. Okay? Or you could do it from the troughs, it wouldn't matter, but it's going to be exactly one wavelength. And the whole thing moves with the speed, and the speed here for light is c, which is the speed of the propagation of the wave. All right. We also can measure the amplitude of the wave, which is how big the oscillation of the waves is. Now, when we talk about waves, what waves really do, and the same thing, think about like water waves. Water waves move, they move up and down, but the water doesn't really move the whole distance. The water just goes up and down, but the wave propagates through the water. Okay? What the wave is doing is taking energy from one place and transporting it to another place. That's what light is. Light is actually just energy. And that energy gets transported from one place to another through the oscillation or the wave. And it goes all the way until it runs into something. There's nothing that stops it. All right, so we have our light and colors. Now we've got to think about colors. Well, colors have to do with the way our eye interprets light. And what they found is that the visible part of the spectrum, the part that we see, actually can be split up into different colors, because that's how most people interpret it. In fact, what we're really talking about is our eyes are light interpreters. And so we see colors. We have red, orange, yellow. I should switch colors here. Green, blue, and violet, which is our spectrum that we see with our eyes. Now, we normally don't see those colors. Like coming from the sun, we see white. And most light we see is white. But if you take something like a prism here, here's my prism. This is an equilateral prism, meaning that it's got an equilateral triangle on each side. But when I pass light through this, like sunlight, then the light gets split up into its individual colors. And they discovered way back around this time too, that white light, the light coming from the sun, was actually composed of all these colors. And they knew about glass and how glass would actually separate out the colors, and they knew about rainbows, but they didn't realize that all of them together made white light. To prove that, they actually had to use a prism, spread them out into their colors, and then if they used another prism flipped the other way, they could put the colors back together and it would come out as white. And they realized, oh, white is the combination of all these colors together. Now what we know is that for us, red has a longer wavelength. And the shortest wavelength that our eyes can see is violet. notice here, and this is one of these weird historical events, red, orange, yellow, green, blue, violet. Lots of times they teach people this as Roy G. Biv, and they put indigo in here. Why? Well, because this is 6 colors, and this came from Newton as well. And Newton realized 6 is not a good number. He was into numerology. There are special numbers. 7's a special number. And because we have 7 days a week, and 7 shows up in all kinds of places. And so he wanted to have 7 colors, so he added indigo in here. But really, all colors of the spectrum, every color you can make is in here. Because it's not just red and orange, and red fades to orange, which fades to yellow, and so on. But really, there's only 6 distinctive color bands when you look at it. All right. We also have something called frequency. Frequency is how many times a crest a wave crest passes a certain point in a given amount of time. And you got to kind of think of it like this. Let's say this is a water wave. If I'm standing here, the waves are coming. I can count and say, oh, in 1 minute, I can count how many waves come by in 1 minute. Usually we do it for waves, we do it in seconds. And so the unit of frequency is actually 1/seconds. And we do frequency as the Greek letter nu. It looks kind of like a V that's been kind of pushed to the side. That's called nu. And that is usually measured as 1/seconds, which we call a hertz, named after the German physicist who studied this. Hertz, and you're familiar with this, you didn't know that. When you do like dialing your radio and you go to 103.2 or something like that to listen to a radio station, it's actually MHz, that's megahertz, which means that's 103 million waves come by every second. And when you have your cell phones now, when they talk about 3G, 4G, and 5G, that's 3 billion hertz, 4 billion hertz, and 5 billion hertz. So that means there's more waves coming by per second. You can actually have better signals. Now they don't go as far, they don't transfer as far, so 5G signals are really outstanding if you're close. But if you're a long way away, the signals don't go as far as they would if they're a 3G signal. All right, so how are all these related? 2 equations I want you to know. Energy is equal to h nu. Remember we said light is just energy. H is a constant. This is called Planck's constant. He was another German physicist. And nu is the frequency. Now I'm not going to make you do any mathematics with this, but I want you to know the relationship here. Meaning, if we have higher frequency, we have higher energy. And vice versa. These are directly proportional. This is just a number. Okay? So this means higher frequency, higher energy, lower frequency, lower energy. And the wavelength times the frequency of a wave is equal to the speed, or in this case, the speed of light. So the speed of light is equal to the wavelength times the frequency. So what's that mean? Speed of light is a constant. It doesn't change. So if I make the wavelength bigger, the frequency has to get smaller, so it still multiplies to make the same value. So these are what we call inversely proportional. So when you have a long wavelength, you actually have a short frequency and lower energy. Over here, we have a higher frequency and higher energy. So for our visual spectrum, the highest energy light that we can detect with our eyes is violet. The lowest is red light. Now, how does our eyes detect light? Well, the detection of light with our eyes is kind of complicated, because our eyes are a chemical-electrical interaction here. And that chemical-electrical interaction makes some weird things happen occasionally. You can overload it essentially. And so let me just show you a little slideshow I made here. So let me turn this on. And what happens is, when you look at something with your eye, your eye has these receptors in it. It has rods and cones. The rods are for detecting essentially black and white pictures, and they're very good for low light. And when you're at night and when the lighting gets very low, you lose all sense of color, but you can still see shapes and stuff. That's when your rods take over. Your cones can actually detect color, and it detects color by a light wave coming in through your eye. It hits a receptor on your back. It hits that cone. That cone says, here's a one of just the right wavelength. So if I have a blue receptor, your eyes actually have 3. Your eyes have a red, green, and blue. And a combination of those means we can see millions of colors. If it's a green wave, comes in, hits the green receptor, it emits a chemical, and then that chemical gets picked up by the receptors in the back of your eye, on the retina, takes an electrical signal to your brain interprets it. Alright, so what we're going to do is we're going to overload your senses. So just stare at this dot in the center here. Now the dot here is purple on the projector here, but with your computer screen and whatever you're looking at, it may look slightly different, but just stare at it. The key is when you stare at it, then those detectors keep putting out all these excess chemicals and say, oh, that's all the same. And if you don't move it around to different parts on your eye, then it's going to overload it. And so what happens is, keep staring at the same spot.